Doing all right? All right. Well, yeah, we have our exam tomorrow, so that's in F112, or it's just 115, right? Sorry, F115, Forum 115. Okay. That's from 1 to 2. And again, if you're online and you can't make it at that time, just send me an email and we'll make other arrangements. All right, well, we'll keep going then. So what we've got here is biaxial strain, and we went through a process here to develop these equations that we use, and they're shown up there. Those are the main ones that are used. So what we've got are equations that are similar to the biaxial stress equations, but they apply to strain. And they're similar in what they do, in that if you know the strains in the x and y directions, you can find the strains at a given angle. They're also similar in form. Okay, so what I have there are equations 71 and 2, which are for normal strain and shear strain. They're on the back of the formula sheet. You'll notice they're quite similar to equations 25 and 6, which are for stress. Okay. There are some differences. There's some factors of 2 in these strain equations that are not present in the stress equations. But other than that, they're quite similar. There is another difference, and we'll get to it a little later, but the angle, the reference angle, is measured from the horizontal plane now. So it's different than stress. Stress is measured from the vertical plane. That's the reference plane. But for strain, the horizontal plane is the reference. And there actually is a reason to that if we have a chance, we'll touch on later. But you want to remember that. One other thing to remember here is this this kind of related topics of a change in angle of a line, which we call alpha, and that's equation 77. That tells you how much a line would rotate. Okay, so if you've got a given angle theta and you throw it into this equation, you know epsilon x, epsilon y, and gamma xy, you can figure out if you have some line that is at that angle theta right there, how much it would rotate to a new position. So it's going to rotate about that point there, how much it would rotate. Okay. Now, if you look at the angle alpha, and then you also look at the angle beta, which is 90 degrees off of alpha, and look at how that line would rotate, if you combine those effects, you're going to get the change in that angular measurement. And the change in that angular measurement is the shear strain. Okay. So alpha plus beta equals the shear strain gamma at a given angle. That's the relationship there. They're slightly different things. The rotation of a line versus the change of an angle is what those relate to. All right, let's look at some examples of this stuff. We'll look at a few different examples. First thing we'll look at is just kind of just standard type problems you work through with this. Now what I have here is just a list of kind of some of the things you run into here, just some of the main topics that we just went over there with shear strain. So this is in your note packet, of course. 500 is what that is. So let's look at a standard kind of problem you work through on this on 530. So let's say we've got a plate, a square plate, and then we paint in a little square element at a 30-degree angle from the horizontal. And then we apply these strains shown to the plate. Okay, so the strains are shown as dimensions. They're not really quite dimensions, but it's just the typical way they're shown. So this is kind of a schematic sketch that shows you the strains. They're shown here and there and there, okay? So given that, why don't you see if you can fill in this bit over here and also fill in the angle for epsilon x1. So you're looking at the number. That symbol there after the number is mu. That's the metric prefix that means 10 to the minus 6. So rather than writing 10 to the minus 6 all the time, sometimes they just use a mu. And we want to get the number from the sketch. And then you also want to get the sign from the sketch too. So it's a little bit like doing those, filling in the stresses there. You look at both the magnitude, the number, but also the sign. You want to get that from the sketch. So what we have there are just a series of strains that are shown. All right, so what do we got? We got 300. So we've got 300 times 10 to the 6. That's positive because, see, that's getting longer in the x direction. In the y direction, though, that square plate that is initially square is now getting shorter, and that's negative 512. And the shear strain is shown all on one side, which may not be an entirely realistic way to show it. These are more schematic kind of sketches that you can dimension. They're also quite exaggerated in the amount of deformation. So there's the shear strain. And that isn't shown entirely on one side. Really, in reality, it would be on both sides of the angle, as I was just showing you there a minute ago. But just for ease of dimensioning, it's shown as though it's all on one side. Okay, so shear strain actually occurs in some mode like I'm showing you here, where you go from the red to the green. However, to dimension it simply on these schematic sketches, they show it as though it's all on one side. So that'd be 210. And that's 10 to the minus 6. Now that angle is getting smaller, so what does that mean about the sign on the shear strain? If the angle gets smaller, the shear strain is positive or negative? Positive, okay? So positive shear strain means the angle in the lower left-hand corner gets smaller. Now, just kind of as an aside, see where that comes from is if you have positive shear stress, that results in positive shear strain. So here's positive shear stress, tau xy, right there. And then I'll put in all the other corresponding shears of the other two that meet in the corners. See, if that's the shear stress that's applied, which is a positive shear stress, it's going to stretch those corners out and push these corners in, essentially. That's what it's going to do. So you're going to end up with a shape like that. So that lower left-hand corner will get smaller, the angle there. That's what's going on there. Now notice the difference between that more realistic sketch that I just made and the schematic sketch up above. The purpose of the schematic is just so you can dimension things easily, okay? So all the strain is put on one side. It's not really realistic though. Okay. And then we've got the angles that we would use to find epsilon x1, it would be 30 degrees, and to find epsilon y1, it would be 30 plus 90. So that would be 120 degrees. Okay. And this has a lot of similarities with biaxial stress. You want to start with a table with the stuff you need to know, which are the strains in the x and y directions and the angles that you're going to analyze things at. And then you just plug them into the equations. Okay. All right. So then we just plug them in. Okay. And it's just a matter of walking on down through that. So we just plug the numbers in. And again, you know, this isn't, there really isn't a whole lot to it. You're just plugging numbers into an equation. It's just like the stress equations with the one exception on the normal strain that you got a 2 right here. That's the only difference. Okay. So when you find epsilon x1, you get 188 times 10 to the minus 6. That's the meaning of that mu. Now, I don't carry the 10 to the minus 6 and stuff all the way through the equations because it's too messy. So I just put in the numbers, run it, and then put the mu in when I'm done. That's usually what I do. It's very common for these strains to be kind of on orders of 10 to the minus 6. So that mu is seems to be a pretty common thing when you're analyzing this stuff. So that's epsilon x1, and that's for 30 degrees. You notice we're putting 2 times 30 into the equation, 60. Okay. All right, now if you want to find the strain 90 degrees off of that, because we would do that because we're looking at that little element, you just plug 120, and twice 120 is 240. You plug that into the equation, you'll get the strain is negative 400. You can use an alternative equation too, which is very similar to what we were doing with stress. So there's an awful lot of similarities between this stuff and stress. I think of the two, stress is generally considered to be more important. You know, stress has to do with failure and things like that. You know, I have seen these strain analyses come up, you know, as I was mentioning. One of my students was working an internship and they were dealing with like a conveyor that was made of a bunch of rollers like that, and they were putting heavy loads on there, and those rollers were deforming and they were starting to interfere with each other as they rolled. So they did do a strain analysis on that. So it does come up, though I don't think it's as common as the stress stuff. Right, so that's the basics of getting the normal strains there. Axial strains, normal strains, whatever you want to call them. Now there's also a shear strain down there at the bottom. Okay. And that one, again, that's formula 72. You'll notice that looks an awful lot like formula 26, with some exceptions. There's some different signs in there, and there's a lack of a 2, a dividing by 2 on that. But it's pretty close. So why don't we look at the shear strain here? Okay. So you just plug it into that equation, you know, that's really about it. And you get negative 598. So what we've got here is that if you run these equations, you can find the strains at a given angle. The assumption is you know the strains in the x and y directions, so now you can find the strains at an angle. That's the basic deal, okay? Now, we always like to sketch up what's happening here. Strain is very much about deformation, so we can come up with a deformation sketch there. I've got a little element there, the original square element at 30 degrees I've shown in there. So, you know, we could figure out what that might look like after the strains occurred, okay? So what we have there is an element at 30 degrees, so I've just kind of drawn that in there. So keep in mind that this reference angle is no longer with the vertical. With strain, it's with the horizontal. Now, there's two ways to draw this. The first way is more of a schematic sort of way. The general convention is to hold the lower left-hand corner constant and then to draw from there, okay? And so what we would end up with would be something like that. That's a sketch of showing these dimensions. The purpose of this is just to show the strains in their different orientations there. We have the epsilon x1 is 188, epsilon y1 is negative 400, and gamma x1 y1 is negative 598. So in the x direction it stretches and gets longer, in the y direction it gets shorter, and then that angle there, that original 90-degree angle changes. It becomes bigger because a negative shear strain makes for a bigger angle. Okay. Now notice there's no attempt made to hold the scale on these. The purpose is just to dimension them. That's, and you see these in textbooks a lot, just to kind of go over this stuff. If this were to happen in reality, for starters, it would be much, much smaller deformations, okay? But let's ignore that and just kind of draw what it might look like. Let's hold this lower left-hand corner constant. You gotta, when you're drawing up these sketches, you gotta have some point that's a reference point. So I'll go with that lower left-hand corner. Now what's gonna happen is it's gonna get longer in the x1 direction, which would be this way. It's gonna get shorter in the y1 direction, and then that angle will get larger. So the best I could do with that might be, in reality, might be something like that. See, longer this way. It's kind of hard to do this, but something like that. That angle will not be confined to one side, as the sketches show. The only reason they do that is so they can dimension it in one location. It actually would occur on both sides. The two lines would rotate, and that lower left-hand corner angle would get bigger. So this is, I don't know, more like reality. It's still not to scale, but it's still, it gets a little bit more realistic picture of what would occur, okay? All right. So the purpose of these equations is to predict how something will deform. If you know how it's going to deform in the x and y directions, you can, using these equations, predict how it will deform at other angles. All right. So let's look at a couple other examples. I probably won't go too deeply into this because I don't know if it can take a fair amount of time and it's not worth a huge amount of time. But let's have a look. So this is just a couple examples. My hope here is just to make this a little bit more concrete or tangible or whatever you want to say. And the other thing is, okay, so let's look at this one. This is page 510. Sometimes I ask myself, I'm a civil engineer and I've done projects kind of out in the sticks, dirt and mud and rocks and moving stuff around and all that. And sometimes I wonder, these fancy equations, do they really work? I mean, I'm running all these really crazy equations, but I've got a bulldozer out there pushing dirt around, and there's a little bit of a disconnect between the two things. So let's kind of look at this and see, if this equation really works. Okay, so let's have a look. And do keep that in mind when you're working, right? Civil is much more about bulldozers when you do the work than it is about running fancy equations forever, okay? Always keep that, just always remember, there's a bulldozer out there pushing dirt around, and it's not a nice, clean, six-figure accuracy number. You're pushing dirt around with a bulldozer is what you're doing. So always kind of keep that in mind, That's important. We learn all this stuff and we apply it, but it's not perfect. These models we come up with, they're not right on. I mean, it's a little different world when you start building stuff. Okay, so let's see, but let's have a look, and let's just test this thing and see if it actually works, okay? All right, so what I've got here on this first one, 510, is I've got some conditions here. So I've got epsilon x, epsilon y, and gamma xy, okay? And those are given. So that's how these biaxial equations start. So I got 0.0667 for epsilon x and y, and gamma xy is 0.2. Now what I did, I drew a square there, a perfect square that's 15 little boxes by 15 little boxes. So that made me, on account of that, I can also express these as fractions, and they may be a little bit easier to figure out how things would deform. So 0.0667 as fractionally is 1/15th, and 0.2 is 3/15ths, okay? And I'm doing that because the square I drew is 15 little boxes by 15 little boxes, okay? Now, let's say that we know that these are the strains that we're applying in the x and y directions. And if that's the case, let's predict what the strain would be at 45 degrees. Okay? And so the equation that I would use to predict the length of that line that goes diagonally across that box at 45 degrees is the normal strain equation. So if I plug in epsilon x, epsilon y, gamma xy, and that 45 degree angle into this thing, it should model how much longer that line gets after these strains are applied. So let's see if that works, okay? Now keep in mind that these equations were developed for very small strains. You know, 20% strain is just huge for most engineering materials. So we might have a bit of inaccuracy with this just on account of the scale of these numbers we're putting into the equation. But all the same, hopefully it'll come out in the ballpark. So let's give it a run, okay? So let's plug these numbers into the normal strain equation and see what comes out, okay? So I'm going to plug those numbers in, and I run the numbers, and what I get is that the strain on the 45 degree angle, and keep in mind that the reference plane for strain, normal strain, is the horizontal, or any kind of strain is the horizontal plane. So this would get us to our diagonal that runs diagonally across that box. And when I run those numbers and plug in 0.0667 for epsilon x, 0.0667 for epsilon y, and 0.2 for gamma xy, and a 45 degree angle, and I run them, what I get is 0.1667. Okay? So that's what this model predicts the strain will be at 45 degrees. So what I've drawn down there below then is an original solid square. And then after these x and y strains are applied, I've got the dashed square, which isn't a square anymore, it's a rhombus, I think now. Okay, so let's look at how I drew that, that dashed box. It's similar to what I was doing a day or two ago with that rectangular plate that we were looking at. It's the same idea. I'm straining it normally in the x direction, 1/15, which is 0.0667. So that'd be one box out of 15. I'm doing the same thing in the y. And then for the gamma, I'm going 3/15, but I'm doing half on a side. So I'm going 1.5 boxes off the x-axis and 1.5 boxes off the y, because the original square there is 15 boxes. Okay. So what's going on here? To draw this thing up, in the x direction, I'm going one box out for 1/15. I'm doing the same thing in the y. And then I'm kicking over, on account of the shear strain, 1.5 on both sides. And that gets me that angular change of 3/15. Okay? So that's what I'm doing. So that's 1, 1.5, 1.5, and 1. And my original lengths here, if you'll notice, are 15. So in the x direction, I'm stretching out at a ratio of 1/15, which is 0.0667. I'm doing the same thing in the y. And then what I'm doing there is I'm taking 1.5 on both sides, and that gets me 3. And then my original length was 15, so that's 3/15. So that's that 0.2, which is gamma. That's what I'm doing. Okay, y'all good with that? Okay. And that's the dashed box. And what I'm going to do, I'm going to see how that affects the length of the diagonal. Okay. So I'm going to look at L45 now at 45 degrees. My original length, if you can read that scale, a little bit fuzzy there, but it's about 10.8 centimeters plus or minus. That was the original length on the solid square. Okay, so this thing's marked by 10, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 10, and not quite to 11, so that's about 10.8, 108 millimeters, I think, 10.8 centimeters, okay? And then I'm going to measure the dashed line next. Okay, so that's 10.8. Now what this model predicts is that if I take that 10.8 centimeter line, multiply it by 1 plus the strain, as we did a couple days ago, I'll come up with 12.6 centimeters. That's what this model predicts that the diagonal will be, 12.6 centimeters. Y'all with me there? Okay. And let's kind of have a look and see if that works out, okay? does this model work? And actually, that's pretty darn good. See, there's 11, 12, there's 12.5, just a little bit more than 12.5. That's pretty darn good for the amount of strain we're throwing into this thing. Okay. So that's what these equations do. If you know the strain in the x and y directions, you can figure out the strains that will occur at an angle. Okay, that's the purpose of this, for whatever that's worth to you, whatever you're trying to do. Okay? We good? Okay? Good. And I got that little derivation here of finding the final length, if you know the initial length and the strain. I just put that in there just to remind you of what I'm doing with right here. Okay. Okay. So there you go. So at 12.6 centimeters on the diagonal, that worked out pretty well, okay? Questions on that? We good? All right. So that was fun. Let's try it again here. Let's do 520, okay? Let's take a square and let's stretch it out. And let's draw a diamond in there, and let's see what happens to the angles in that diamond when we stretch out that square. So again, I'm greatly exaggerating this so that we can see kind of what's happening here. So what we're going to do is we're going to take that square, we're going to stretch it into a rectangle. Okay, epsilon x will be 0.25, epsilon y will be 0, and gamma xy will be 0. Okay. So what's going on there is I've got the original length there of 2. So L0 is equal to 2. Delta is equal to what? 2.5, because I've stretched it out to 2.5. So delta is 0.5. So epsilon is delta over L, and this will be in the x direction. That's going to be 0.5 over 2. So epsilon x is equal to 0.25. That's how I'm coming up with the 0.25. So what I have here, let's look at some of these things. Let's look at the angles and what happens to them when you do that. Okay, let's predict what will happen to the angles. Let's run for 45 degrees. Let's run the shear equation and the alpha equation for 45 degrees. So let's go ahead and put those in there. Okay, so when I run the shear equation for 45 degrees, I got 0 for epsilon y, 0.25 for epsilon x, and 45 degrees. Gamma is, xy is also 0. So when I plug that in, I get gamma is negative 0.25. Now 0.2, now what comes out of that is an angle in radians. So I'm going to convert that to degrees. That's 14.3 degrees is what it is, okay? That's 0.25 radians. Now what alpha comes out to be is half that, negative 0.125. So that's 7.2 degrees. So what I would expect is that original angle ABC should change by 14.3 degrees. It's a negative, so that means that original 90-degree angle should get bigger. It should be about 90 plus 14.3. So I'd expect that to be 104.3. Okay. Now this line that is BC should rotate clockwise because it's negative. So clockwise 0.125 radians, that should be 7.2 degree rotation. So let's have a look and see if that happens, okay? So that original angle ABC was 14.3 degrees. Now I've got a negative shear strain. Now keep in mind that negative means it gets bigger. So 90 plus 14.3, I would expect that new angle to be 104.3. Okay. And again, I know this is hard to read, but there's 90, there's 100, and there's 105. I'm a little bit short, but not too bad, you know, considering we're throwing just huge strains into this. I don't think that equation is really meant to model 0.25 for strain. That's just so large, okay? But it's not bad, okay? Again, it's predicting what's going to happen. If I know what's happening in the x and y directions, I can predict what will happen at an angle. Okay, so that original 90-degree angle ABC is now about, it looks like about 104 degrees, something like that, a little short of that, but in the ballpark, okay? It's reasonable. Okay? So I just want to illustrate to you what these equations mean. That's all I'm trying to do here, okay? It's kind of like when I was showing you those failures, you know, at different angles. It's the same idea. I'm just doing it for strain now. I'm just trying to illustrate it. Okay? All right. And then similarly, that line BC is supposed to rotate 7.2 degrees, okay? So there you go. So it was at 45. So over here on the left, BC is at 45 degrees. Now it should be at 45, but it's going to rotate clockwise, so that'll make it less. So what is that, 37.8 degrees? That's what I would expect it to be now. Something like that. And you know, it's not bad. Here's 30, here's 40, it's 35. So it's about 38. So it's, you know, not exact, but all the same, not bad, okay? So that's the meaning of this biaxial strain. It's showing you what's happening at different angles. That's the purpose of it. All right, so that's a little bit on the biaxial stuff. So we got questions on it? All right.